All right, let's talk about plasma. You know, it's not just the fourth state of matter, it's pretty much the most common stuff in the entire universe. But it's got this, well, this really strange secret. In this explainer, we're going to pull back the curtain on how this huge sea of electric charges manages to hide its own power. It's fascinating, so let's dive right in.
Okay, so here's the big puzzle we need to solve. Think about what plasma is, right? It's basically this super hot gas, a wild soup of positive ions and negative electrons just flying around. Now, with all those charges running loose, you'd think it would be just crackling with these powerful, long-range electric fields. But it's not. Look at it from a distance, and it acts almost completely neutral. So what gives? How on earth does it pull off this incredible magic trick?
Well, the answer is all about this amazing collective behavior.
And that behavior is called the shielding effect. This right here, this is the core idea that explains how a whole sea of charges can look so calm and collected from the outside. Now, you can look at this in a couple of ways. On one hand, you could just say, well, plasma is a great conductor, so any electric field gets shorted out right away. And you wouldn't be wrong. But there's a much deeper, more powerful way to see it. It's better to think of it as a dielectric phenomenon, where the plasma itself is actively, physically reorganizing to cancel out those fields from the inside.
And this whole self-organizing process has a name: Debye shielding. You gotta understand, this isn't just some random thing that happens. It is the defining behavior of plasma. It's how plasma polices its own internal world, screening out and hiding any stray electric fields to keep things neutral on the outside.
So how does this actually work? What does it look like? The best way to get it is to just watch it happen. So let's build one of these shielding clouds together step by step. We'll just imagine putting a single charge right into a peaceful plasma. Okay, let's see it in action. So picture this. We start with our nice, balanced, quiet plasma. Then bam, we drop a single positive charge right in the middle. What happens? Well, the plasma reacts instantly. All the nearby negative electrons, they rush in, attract it to our little intruder. And the other positive ions, they get pushed away, repelled. So what you get is this shielding cloud of negative charge that forms right around our original positive one. And the result is pretty amazing. If you're looking from far away, that negative cloud completely cancels out the positive charge inside. It's basically invisible. It's been shielded from the rest of the plasma. And this isn't just a handy way of thinking about it. No, the actual physics tells us that the original charge is literally shielded by this cloud of opposite charges. The really important thing to get here is that the plasma is not passive at all. It's an active participant rearranging itself to neutralize anything that tries to disturb the peace.
So, we get how the cloud forms now. But that just leads to the next big question. How big is this cloud? Are we talking about something tiny, like millimeters? Or huge, like meters? Or even bigger? Well, it turns out there's a very specific measurement for this effect.
And that special ruler is called the Debye length. And it's way more than just a measurement. It's like a boundary line. It tells you the exact radius of that shielding cloud we were just picturing. It defines the personal space bubble around a charge before the rest of the plasma just makes it disappear from view. In the world of physics, we use the symbol lambda d. And trust me, this little number is a huge deal in plasma physics. It tells you the exact distance over which any single charge can even have an influence before the rest of the plasma just completely smothers it. It's our official shielding ruler.
And the effect is, well, it's really dramatic. If you're inside that Debye length, inside the cloud, you absolutely feel the strong pull of that original charge. But the second you step outside that bubble, the influence just plummets. It drops off so fast, the shielding is so good that the charge inside effectively vanishes.
And look, this isn't just some quirky little thing that happens sometimes. This is a fundamental rule for all plasmas. It governs everything from how we build fusion reactors right here on Earth to how the solar wind works, all the way out to the behavior of those giant gas clouds between the stars. It is everywhere. But here's where it gets really interesting and a little tricky. What if you have a really thin, sparse plasma? One where there might only be a few particles inside that whole shielding cloud. Does the whole thing still work if the cloud isn't some dense physical wall? And the answer is a big, loud yes. This is absolutely key. The shielding effect is all about statistics. It's not about building a solid wall of electrons. It's just about changing the probability of finding an opposite charge nearby. And even a tiny shift in those odds is more than enough to create the shielding effect on average. Okay, so let's wrap this all up. What did we learn? First, plasmas are not passive at all. They're actively working to hide their own electric fields. Second, they pull this off using a process called Debye shielding. Third, they do it by building a shielding cloud of opposite charge around any intruder. And finally, the size of this whole operation is perfectly defined by one simple ruler, the Debye length.
So in the end, what seems like a simple hiding trick is actually something way more profound. It's not about building walls. It's about shifting probabilities. The fundamental rule that keeps the most common state of matter in the universe in check is, when you get right down to it, just a beautiful, elegant game of chance.